Guys, you want to create the best model, but building deep learning models has many challenges. In this video, we'll train a deep learning model and discuss how to improve the model's performance with normalization and standardization. Let's use the NIST dataset to demonstrate this. The NIST dataset consists of images of 28 by 28 numbers. This dataset is built in TensorFlow, so we can import it easily. For this, let's import TensorFlow and Keras. Let's import TensorFlow first. And then, let's import Keras from TensorFlow. Nice, we have imported our necessary libraries. Now, let's import the NIST function to load the dataset. Let's get the NIST function from TensorFlow.Keras.Datasets class. Then, let's load the training and test data using this function. Let's write the xtrain and ytrain datasets first. And then, let's write the xtest and ytest datasets. Next, let's type NIST and call the load data method. Cool, we've created our datasets. Let's look at the structure of these datasets. After typing print, let's write the training input dataset first, and then, the training output dataset. Then, after typing print again, let's first write the test input dataset, and then, the test output dataset. As you can see, the training datasets consist of 60,000 samples and the test datasets consists of 10,000 samples. Awesome, we looked at the structure of our datasets. Let's go ahead and build a deep learning model. To do this, we can use the sequential technique in Keras. After writing the model, let's call the sequential from the tf.keras.models class. Now, we can write our layers inside this class. First, let's write the flatten layer. Note that, this layer converts two-dimension images to one dimension. It's time to call the flatten layer from tf.keras.layers. And then, let's write the input shape parameter, and pass the size of the inputs to this parameter. Now, let's write the first dense layer. This layer will be our input layer. Note that, the neurons in the dense layer are connected, with all the neurons in the previous layer. It's time to call the dense layer from tf.keras.layers. Let's pass 512 neurons to this layer. Let's give ReLU to the activation parameter. Cool, we've created the input layer. Now, let's create the first hidden layer. Again, let's call the dense layer from tf.keras.layers. Let's pass 512 neurons to this layer. Let's give ReLU to the activation parameter. Awesome, we wrote the hidden layer. Now, let's create the output layer. Again, let's call the dense layer from tf.keras.layers. Since there are 10 categories in our outcome variable, let's write 10 neurons in this layer. Since our problem is a multi-category classification problem, let's use softmax as the activation function. Great, we've built our neural network model. Now, let's go ahead and compile the model. As we compile the model, we specify the loss function, the optimizer, and a metric to measure the model's performance. Our problem is classification, right? So, our result variable consists of numbers from 0 to 9. There is no such thing as big or small among these numbers. These numbers are just labels. For the program to understand this, we need to convert these labels to one-hot encoding. We can do this with the tocategorical method in Keras. But, there is an easy way. That is, we can use the sparse categorical cross-entropy loss function. Let's write our model variable, and call the compile method. And then, let's write sparse categorical cross-entropy to our loss function. Next, we can use the atom optimizer for the optimizer parameter. Finally, we can set the accuracy for the metric parameter. Nice, we've compiled our model. Now, let's move on to model training. To do this, we can use the fit method. Let's write our model variable, and call the fit method. After that, let's give the input and output training datasets to this method. And then, let's set the number of epochs to 10. This means that, the whole dataset will go through the model 10 times. When we run this command, training starts. If you notice, the loss value of the model decreases in each epoch. This means that, the model learns from the data. After 10 epochs, the accuracy was 97%. Note that, the closer this value is to 1, the better the model. Okay, we've built a good model. But, we can improve the performance of this model. The images in our dataset consist of integer values from 0 to 255. When you look at the weights and biases of the model, you will see that it consists of small numbers between -1 and 1. The inputs go to the output layer, multiplied by these coefficients in the layers. Since the values in our dataset range from 0 to 255, matrix multiplications yield large results. This both slows down the training of the parameters, and makes it difficult for the parameters to reach the optimum value. To overcome these problems, we can normalize the data. Normalizing means bringing the data to a certain range, such as 0 and 1. The values in our dataset ranged from 0 to 255. We can divide this data by 255, to get it between 0 and 1. By default, parameters in the Keras model are 32-bit floating numbers. So while normalizing the data, we can also convert the data to 32 bits. First, let's import the NumPy library. After writing xtrain, let's write the training input variable, and divide this variable by 255. And then, let's call the asType method, and convert the data to float 32. Let's do the same with the test input data. After writing xtest, let's write the test input variable, and divide this variable by 255. And then, let's call the asType method, and convert the data to float 32. Cool, we normalized the training data. Now, let's train the model again with this data. For this, let's copy and paste the commands we used for training here. Now, let's run these commands again. The model started retraining from scratch. As you can see, after 10 epochs, the accuracy of the model increased to 99%. This accuracy is better than the previous accuracy. So, we improved the performance of the model a little more. It's time to see the performance of the model, using test data. To do this, we can use the evaluate method. First, let's write the model variable, and then call the evaluate method. Next, let's pass the input test set, and the output test set to this method. It turned out that, the accuracy of the model on the test data, was about 98%. This value is slightly smaller than the training accuracy. We want the training and test accuracy values, to be very close to each other. Another way to bring data into a certain range, is standardization. If your data is normally distributed, it is better to standardize the data, to build a good model. But note that when standardizing data, you must first calculate the mean, and standard deviation of the data. Let's do this with NumPy. Let's first take a variable named mean, and find the mean of the training data, with the mean method. Next, let's take a variable named std, and find the standard deviation of the training data, with the std method. Nice, we've obtained the statistics of the training set. It's time to standardize the data. For this, let's write the xtrain variable first. Next, let's subtract the mean value from the training data, and divide it by the standard deviation. Lastly, let's convert the result to float 32 with the asType method. Since we normalized the latest data, let's reload the original data. Cool, we have standardized the data. Let's go ahead and train the model again. To do this, let's copy and paste the commands, to rebuild and train our model. When we run these commands again, model training starts. Here, you can see the accuracies after each epoch. After the latest epoch, model training is again 99%. As you can see, the performance of our model is better than the performance of the model we built with raw data. In this video, we discussed how to improve the performance of a model with normalization and standardization techniques. That's it. I hope you enjoy it. Don't forget to subscribe, hit the bell icon, and like the video. We also create content on our other social media accounts. We will be happy if you follow us. Thanks for watching. See you in the next videos. Bye for now.